and we'll move to the next talk, which is the title is Ireland, an MILP-based algorithm for learning interpretable input-output relationships from binary classification data. And the talk is going to be given by Marleen Balvert. I would ask the people in Vienna to start the video. Thank you.
Good afternoon. Welcome to this talk about Ireland. Now you may think, Ireland? Is this going to be about orange and green, about clovers, leprechauns, harps, maybe some beautiful nature? It is not. This talk is about an algorithm called Ireland, the iterative rule extension for the logical analysis of data. Now, before we go into the algorithm, let's have a look at motivation. You may be familiar with this distinction. There are two types of models for classification or prediction. One type are called white box models, and these models, they do not just give you the classification or the prediction, but they also give you an interpretable input-output relationship. However, they can handle only small amounts of data. Then on the other hand, there are the black box models, such as deep neural networks. They do not give you an interpretable input-output relationship, but they do give you a good prediction or classification, even if the data gets really large. Now, Ireland is developed to identify interpretable input-output relationships, even for large data. And in particular, we're going to look at a specific type of input-output relationship, namely Boolean phrases in disjunctive normal form. And they look as follows. If a sample satisfies all of the first set of characteristics, or they satisfy all of the second set of characteristics, or they satisfy all of the third set of characteristics, then the sample is classified as a case, and else it is classified as a control. Now, why use Boolean phrases? Well, first of all, because these have been shown in a previous study that they are very easy to interpret. They are one of the easiest ways for us humans to understand an input-output relationship. And second, my work always focuses on biological data, on genetic information. And these models, Boolean phrases, they support underlying biological knowledge. Now, genetics data is often very large, which is why I wanted to develop a method that can identify Boolean phrases in disjunctive normal form from large amounts of data. So that is the goal of today, to present you with an algorithm that can identify these Boolean phrases in DNF from large data. All right. Now, first of all, let's just see how you generally identify Boolean phrases in disjunctive normal form. This has been done before, especially the group of Peter Hammer has done a lot of work on this, but I will use the formulation by Joao and Nijnenberg. Now, what we can use is mixed integer programming, and these models decompose Boolean phrases in DNF into various AND clauses. And then the integer program needs to decide for each of these AND clauses which features are going to be included. And for that, the integer program uses the variable sjk. Now, sjk is a binary variable which is equal to 1 if feature j is an AND clause k, and 0 otherwise. Now, once we know which which features are included in each clause, then we can also determine for each of the samples which clauses they satisfy. And for that, the mixed integer program uses variables t and k, which are equal to 1 if sample n satisfies clause k, and 0 otherwise. Now, then finally, each sample that satisfies at least one AND clause, or for which at least one t and k is equal to 1, can be classified as a case, and otherwise it is a control. And for that, we use binary variables y hat n. Now, there are constraints that can be formulated such that these variables take on the right values, and then the objective of the integer program is to minimize the classification. Now, this model is really large. In fact, it has 2 times the number of features times the number of clauses, variables s. It has number of samples times number of clauses, variables t. And it has number of samples, variables y hat. And it is particularly this multiplication with k that makes this a large number of variables that is difficult to handle. Now, for that, Already in the literature, there are 2 papers using column generation or an iterative rule extension. And what they do is, you're starting with a pool of AND clauses. A master problem selects those AND clauses that together form the Boolean phrase that yields the lowest error. Now, using a subproblem that computes the reduced cost, as in column generation, a new AND clause can be generated that is promising and that is added to the pool of clauses. Now, of course, keep on iterating until no new AND clauses can be found. Let's have a look at the subproblem. Here you see the variables that we had before, S and T. But if we're generating only one clause, then the subscript K is not needed anymore. So we only have number of features plus number of samples variables left. And this really helps. Now, the subproblem minimizes the error. Of course, there are some weights related to the shadow prices in the master problem, and there are constraints that ensure that S and T take on right. Now, in Ireland, we're going to do this a little different. Instead of minimizing the error, we maximize the number of cases that are classified as a case. And for the controls, we place an upper bound on the number of controls that is allowed to be classified as a case. So an upper bound on the number of false positives. You may wonder why we do this. We'll get back to that at the end of this talk. So this is a subproblem that Ireland uses. And then we can do the same procedure as before. We generate a pool of AND clauses, and each of these AND clauses satisfies this upper bound on the number of false positives. And then we solve a master problem. Now, also this master problem does not minimize the error. It maximizes the number of true positives while restricting the number of false positives. Then we solve the subproblem again, add new AND clauses to the pool, etc. And we do this for various upper bounds on the number of false positives. All right. Now, this subproblem is still quite large because it has number of features plus number of samples variables, and this number of samples can get prohibitively large. But we do not maybe need all the samples. Look at this example over here. Here we see 2 AND clauses, 6 cases, 6 controls, and the orange dots indicate for each of the samples which of the clauses they satisfy. And then overall you can make a prediction. Each sample that satisfies at least one of the clauses is predicted to be a case, hence a green dot, and the others are predicted to be a control, hence a white circle. Now, if we add another clause, for example, this one, well, for this clause, we see that nothing changes, right? Because the samples satisfying this clause, namely cases 2 and 6, already were classified as cases. So this doesn't mean anything. Adding this clause is useless. Adding this clause, however, where case 5 satisfies clause 3, definitely makes a difference for the prediction, because now we have an additional case classified as a case. So overall, we only need to include cases 4 and 5, because cases 1, 2, 3, and 6 were already classified as cases anyway. We do, however, need to include all the controls, because if you do not include all of them, well, then the upper bound on the number of false positives doesn't make sense. All right, so this means that we do include all the controls in the subproblem, but we only include those cases that, without the new clause number 3, were not classified as cases yet. And this subset of cases, we call this N-1. Now, N-1 in the first couple of iterations, of course, is simply all the cases, because there are no clauses yet, or very few. So only very few are classified as cases. So we set a fixed size for N-1, which means that we need to randomly sample from the cases if the number of cases not yet classified as cases is too large. If this number is smaller, we still add additional cases to N-1 to always have the same size of N-1. That brings us to the subroutine of Ireland. We start with a pool of AND clauses, satisfying the upper bound on the number of false positives. We solve the master problem, the new master problem, and then we randomly select subsets of cases N-1. And we do this multiple times using parallelization. parallel computing to be exact. Now for each of these subsets n hat 1, we solve the subproblem, and then this gives a set of new AND clauses that are added to the original pool of AND clauses. And we go back to the master problem, and we keep going. Now this is a subroutine, and a subroutine is solved for multiple upper bounds. And once the subroutine for all of these upper bounds, the stopping criteria, are satisfied, then we combine those pools of clauses into one huge pool. Using this pool, we can solve the original master problem, so the master problem that minimizes the error. Then again, we check some stopping criteria. If they are not met, we go back to the subroutine, solve it for multiple upper bounds on the number of false positives, back to the master problem, etc., until the stopping criteria. This is Ireland. Let's have a look at some results. In this figure here, this is going to be a scatter plot. So you will see dots, and each dot represents one data set. And on the vertical axis, you see the objective value that we obtained with Ireland, which of course should be as small as possible. And on the horizontal axis, you see the objective value obtained with the original integer program. And these are the results we got. You see that there is a cluster of data sets for which Ireland is better. There's a cluster of data sets for which the original integer program was better. But most striking here is this pile all the way on the right. Now these are data sets where the original integer program ran out of memory, so it could not find any solution at all, and that's why we assigned it an objective value of 1. Ireland, however, was able to find a solution for these data sets. Then we can also look at the runtime, which you see over here. And again, there are data sets where Ireland has a better runtime. There are data sets where the original integer program has a better runtime. But what you see again on the right is very striking. These are the data sets where the original integer program ran out of memory, or where it couldn't find a solution within 4 hours. It couldn't finish. As you can see, Ireland always finished within 4 hours, mostly even in at most 2 hours. Now, of course, you want to know in advance for which data sets you should use Ireland and for which you should use the integer program. And the answer is actually quite obvious. Here you see 2 histograms, and each bar you see represents a number of data sets. The black bars show the data sets where the original integer program was better in terms of objective value. The light gray bars show the data sets where Ireland was better, and the dark gray bars, there was not really a difference. And as you can see, as n gets larger, more often Ireland is better, especially when n is larger than, say, 2,500, I would use Ireland. And something similar holds for the number of features. As the number of features grows, Ireland gets better. And this makes sense, right? Because we only needed Ireland because we wanted to be able to handle large data sets. If we now look at the runtime, we see an even stronger pattern. As the number of samples or the number of features gets large, you need Ireland to solve the problem. For small data sets, just use the original integer program. All right, so that's very nice. But now you're still stuck with the question, why use these upper bounds on the number of false positives? Well, that is because in practice, what you often would like is not just one answer, because that gives you a weighted sum of the errors for false positives versus true positives. What you really want is a trade-off between false positives and true positives. Or in other words, a trade-off between sensitivity and specificity. Now, using this huge pool of AND clauses, where each of the AND clauses has a different number of false positives, you can use the master problem by varying the upper bound on the number of false positives and inherently generate very easily the trade-off curve between sensitivity and specificity. And here it is. This is an example for one of the data sets. Not a small, not a big, somehow average data set. Well, yeah, reasonably average. Quite large, not extremely large. And you see that there is a very nice trade-off between sensitivity and specificity. And this figure, running both Ireland and solving then the master problem for various upper bounds on the sensitivity, this shows this can be solved within the hour. So instead of just solving one optimization problem in a large amount of time, you could even get this entire Pareto frontier using Ireland. So to conclude, first of all, Ireland speeds up the computation of Boolean phrases in disjunctive normal form for large data sets, yielding lower errors. And a very nice thing is that there is a lot of small subproblems that's being solved in parallel. So if you have multiple cores, the speed of Ireland is very good. Second, because we use these different subproblems, Ireland naturally allows for a very efficient computation of the trade-off curve between sensitivity and specificity, which in reality is often very nice to have. Now with that, I would like to conclude, and I would like to thank you for your attention and be happy to take any questions. Thank you.
Thank you very much for the very interesting talk. Are there any questions? Oh yes, there is. No questions from what I understand. Are there any questions? Yes, there is a question from Vienna, please.
Hello. Thanks for the talk. It was great. I just have a very basic question. So I'm just wondering, in this work, how can you relate to the problem you're solving? Seems very similar to like a decision tree problem or a decision list problem or a decision set problem. Now I was just curious if you can comment on the similarity and whether your techniques can be used for these kinds of problems and vice versa.
Right. Yes. Thank you for the question. So first, let me motivate why I chose to not go for decision sets, but for Boolean phrases. And that is mostly because, first of all, as I mentioned, I work in genetics, and this is a very natural formulation for applications in genetics. And second, there was a paper published 1 or 2 years ago that investigated how easy to understand decision sets were and Boolean phrases. And there it was shown that Boolean phrases were actually easier to understand. So that's why I made this decision. And then can you use this approach for decision sets? I haven't really thought about it before, but given the flexibility of integer programming, I suspect it would be possible to write a MIP that abstracts these decision sets. The only difference being that in decision sets, there's more of a hierarchical structure, right? It's more of a tree-like structure where one builds on the other. Sorry?
But if you consider, for example, decision trees, they seem to be like like the formulation you give. So we could think of decision trees as some kind of disjunctive set.
Right. Yes, but then you do, so one level builds on the next. So you first make a decision that holds for everyone. You need to make the split for everyone.
Mm-hmm. Okay, I see. Yeah,
No,
that's
but the decision, I don't see the difference between. Sorry to interrupt. I don't see the difference between a decision set and the Boolean phrase. Maybe I'm missing something, but for me it's the same.
Yeah. So a Boolean phrase in general, yes, but specifically in disjunctive normal form. So disjunctive normal form allows for this splitting up in 2 levels, just the and clauses and the or combinations of the and clauses. If you build a tree, you have many levels that build upon another.
For a decision set, you just have statements which are the ends, and if you can view them as, well, putting an or. So if any of them fires, it's like the or. Probably there is a difference.
Wouldn't the decision set be like if a statement hold, else? Is that an or is that?
Well, it's out of order, but then if you can do a decision list, right? Yeah, it would be nice to compare with decision sets or decision lists. Decision sets, you're right, there is no order, so you cannot really emulate the semantics that you have, but decision list seems that you can, at least for me.
Yeah, I'm thinking. So if you could indeed make it into a 2-level thing, then I can imagine this master subproblem structure still to hold. If it's more a tree-like structure, that makes it more complex.
If you do the first condition, if it fails, you have the second condition, the third condition, fourth condition. So that's your or like. And then if everything fails, then it's the else, where you can also have the same structure. So maybe I'm missing something of the semantics, or of course doing it without writing, it's difficult. But...
Yeah, exactly. Yeah, so also maybe I'm missing the exact workings of a decision set. So you have the if a statement holds, else. So basically you're saying if the first one does not hold and the second one holds. But it would be nice to write this out and to see how it really works. Yeah.
Okay, are there more questions? Okay, so a quick question, because you are using a mix, from what I understand, you are using a, oh, sorry, there is another question on the test priority. Klaus Vick, please.
Yeah. Do you do some pre-computation on your DNFs to simplify them?
What do you mean by pre-computation?
You can have different types of DNFs. You can simplify them. You can have lots of terms, or so lots of ors, or some, you can do some pre-computation on a DNF to get a DNF with lesser numbers of or clauses.
Right. Would that require you to know the DNF, I guess?
Yes.
Yeah. So here we're learning the DNF.
Yeah, we're learning the DNF, sorry.
Yeah, but you can definitely, there are parameters in here to restrict the complexity of the learned DNF.
Mm-hmm.
Okay. I need to interrupt because we are running out of time. Sorry. So thank you very much for answering the question.